to introduce one of our newest faculty members in KHP, Dr. Van Gogh. And a little bit of background, I would have had to do some weight training to carry in his entire vita, but he received his BS in mechanical engineering from the Department of Aircraft Design and Applied Mechanics in Beijing, China. He received his MS in biomechanics and motor control from Penn State University, as well as an MS degree in mechanical engineering from Penn State. He then completed his PhD at Penn State in biomechanics and motor control, and then completed a postdoctoral fellowship in rehabilitation engineering at the Rehabilitation Institute of Chicago. He's held several faculty positions as well as research associate positions, but we are very pleased that you're here with us now, and we'll have to turn you from a cat into a different kind of cat.
Thank you very much, Dr. Ecclesi, for the introduction. Good morning, everyone. Thanks for coming. My office actually is across the hallway. It's probably the closest one. Yeah. So today I'm going to talk to you a couple of studies we have done before that is pretty much targeting a very special population is a stroke. Anyone has done any study or research on the stroke before? Not many, yeah. All right. So before we jump into the study, just give you some background and introduction. Okay. About the stroke and its impact. And the stroke, we all know, is actually, there's a formal name, right? Officially known as the CVA, right? You probably recognize that term. It's pretty long, but typically people call it stroke, right? And also I show our map here, and with a certain states and highlighted here. And anyone knows the name of the map? There's a pop-up quiz.
Stroke belt. Stroke belt.
There you go. It's called a stroke belt, right? And that means actually those states in the highlighted here and have a significantly higher stroke mortality about the national average. I think it's about 10%, right, of these. So unfortunately, I think Kentucky is one of them, right? I'm sorry about that, but yeah, that's based on the data from the CDC, right? Stroke has a huge impact, right, on the society. So first, the fact is the leading cause of adult disability, right? It's the leading cause. And just to share with you some numbers, about 800,000 new or recurrent stroke each year, right? And again, I can tell you this figure is based on the statistic or study years ago, so it must be jumped higher than that, okay? And currently, there are about 5 million Americans living with stroke. And the last number figure I want to share with you is stroke-related healthcare, and the cost is about $74 billion annually, okay? And just to give you some figures. There are a lot more figures out there, but I just want to highlight the importance, the significance into study or target this particular population. All right. So next, I want to share with you why we are interested in studying this population, okay? And why we're targeting the lower extremity, and more specifically, targeting one particular group of muscles, okay, in this population. Here we go. And before we're talking about mobility, actually, as you all know, I know we got a PT here. Speaking of stroke rehab, right, rehabilitation, and one of the major goals is to improve or restore functional performance, right? But we all know functional performance is a pretty broad term, right? It could include almost everything. And mainly daily activities, right? And among them, actually one of the major or important functional performance is ambulation or mobility, right? Everyone here, I believe, has pretty good mobility, right? You can walk anywhere you want, you know, you can climb the stairs, right, up and down, okay, easily. But that's not an easy job for the stroke population, right? Mobility is important because it's essential to determine the dependence of the person as a human being, right? You agree with that? If we cannot walk, we're not independent, right? However, and a stroke induces a couple of problems. And here we're going to talk about the contractures and or spasticity, right? So anyone that's familiar with those two terms? Spasticity or contracture? Have you heard about that before? Not really. Well, spasticity, you can think about that's kind of like a muscle tone, right? Okay. So it's mainly due to the stroke or other, upper or neural syndrome, right? Okay, cerebral palsy, and it could also be a spinal cord injury. Contracture is a little slightly different, but even sometimes, in the clinic side, and they are interchangeably used or kind of like merged together. Contractures mainly are due to the shortening of the tissue, right? For example, the muscles, the tendon, and so on, or skin. So it's kind of like a permanent or shortening in the soft tissue, right? And these two things actually can cause a lot of problems or consequences, right? And particularly can impact the mobility we're talking about, all right, and walking. And luckily, or fortunately, in the previous studies or in the literature, we can find some promising results indicating that the muscle tendon property actually are related to the contracture and the all spasticity. So that indicates if you got a better understanding of the changes at a muscle tendon level, we can possibly come up with some recommendation regarding stroke rehabilitation. So that's the whole logic behind that, right? Okay. Yeah, now the animation is coming. Yeah, sorry, it's a little dark. But obviously, that's not a stroke survivors, right? It's a healthy person, just like that. Okay, another slide. I just want to show you why we are interested in this particular group of muscle, right? As we all know, actually, we will walk around, ambulate, right? Either walking or running. And this particular group of muscle, we call it calf muscle, right? Or plantar flexors, or tricep shoulder muscles, right? That's the three muscles. They play a very important role, right, during ambulation. And any problem actually are going to see experience out there is going to impact the gait that we're talking about, right? In other words, that we will fit. I'll just give you some examples, right? For example, in the stroke population, typically they have a limited or ankle range of motion, correct? That means actually they cannot bring, for example, the ankle to the neutral sometimes, right? Or less than 10 degrees in dorsiflexion, right? So it's typically how the ankle joint in the plantar flexion. So you can imagine this is gonna impact the gait pattern. As shown here, this is just one example, right? So during the mid stance phase, all right? When the limb actually is on the ground as a single limb support phase, right? And during that particular time window, and because of the limited or range of motion around the ankle joint, and the ground reaction force, it will be placed in front of the knee joint, right? And y'all familiar with the ground reaction force? Okay, that's good. All right. So the ground reaction force actually is gonna causing the knee extension moment, correct? It's gonna force a knee hyperextension. You see that? It's all mechanical problem, right? We can at least interpret that way, right? Okay. Now this is because of the limited range of motion around the ankle joint. A couple of other examples I can show you. Due to the weakness, the plantar flexor, basically, you're probably going to see things like late heel rise, approaching the terminal stance phase, right? They cannot pick up the heel or in a timely manner, in other words. And more importantly, you see that we know that the plantar flexors actually play a very important role in producing the propulsion, right? Propelling the body forward on the accelerated center of mass of the body. And the problem is because due to the weakness of that group of muscle, right? And there will be a lack of propulsion power, right? Generated by the ankle joint. And consequently, it's not surprising to see this group of population walking slowly, right? It's not as fast as we do on a daily basis. Again, we got that animation pop out there, but like I said, you can easily picture that, right? There's a lot of problems, associated with the stroke. In particular, here we're talking about a contracture and spasticity. All right, next we're going to show you a couple of studies. And the first two studies, I'm going to show you the passive and active property in the gastrocnemius muscle, okay, in this group population. So methodology, in this study, actually we recruited 10 stroke survivors, okay, with a spasticity and a contracture around the ankle joint, and have the modified Ashford score more than 1, so there is a muscle tone out there. And for us, healthy population, the score should be 0, right? Okay? If you got anything more than 0, something is going on, right? You got muscle tone, right? And the history of CDA more than 1 year, so that's the chronic stroke survivors. Average age is about 55 years. And then we got a age gender match control group, right? And also I got a 10. And then we use the one particular machine is from GE. It's a very powerful ultrasound machine. So we use that actually to assess the in vivo muscle tendon property in this study. We use the first part sensors to measure the joint, the biomechanics, okay? And we use a lot of even analytic stuff for data acquisition. Next, I want to show you the setup. Okay. So this setup actually is similar to the Biodex, right? You probably have used the Biodex, the similar, but this is a fully customized device in the lab, So we got one motor around the knee joint, another one at the ankle joint. You cannot see that because it's blocked, right? There is also 2 torque sensors. In this case, actually, we don't use the torque sensor around the knee joint because we only use that to configure, the knee at different positions. Okay. So basically, we place the knee joint at a full extension, okay, 30, 60, and 90 degrees in flexion. And for each knee configuration, we also systematically change the ankle position. Okay, there's a lot of combinations, right? But I'm going to show you. And then we have the electrodes, okay, attached on the skin, so we can deliver electrical stimulation. We can activate the muscle, right? All right. And then the torque sensor is going to pick up, any torque generated, induced by this electrical stimulation. And we also use the probe, as I show you, right? We use the GE ultrasound machine, and we can measure, record the in vivo image of the muscle tendon of interest in this study. So here shows the electrical stimulator we use. Okay, this is a programmable. This is actually more powerful than those actually used at home. This is developed or designed for research only. I think it's not even FDA approved. Yeah, sorry about that. Yeah, this is actually manufactured by a company in Europe, I think, yeah. So you have to, it's not easy to purchase that actually on the market, and it's very expensive, yeah. I think it's about $5,000, yeah, for that small machine. But this machine is pretty powerful. You can program that. You can program the, the pattern, for example. You can program all those, the pulse train. You can manipulate that precisely. Okay, that's the reason it's expensive, right? Okay. Okay. Once we deliver that electrical stimulation, you can see that this is just show you some sample or torque signals, right? That would be X, Y, Z. But sure, this is actually our 6-axis, right? It can measure 3 forces and 3 moments or torque in the 3 dimensions. So it's mainly using the robotics. Yeah. Again, this is torque sensor is very expensive. Yeah. So, but very powerful. We love that. Yeah. Okay. And like I said earlier, actually we use the sonography, right? And here shows the diagram. This is actually the real image we capture, during the study, right? So here's the probe. You can place the probe perpendicular on the top of the skin, and you can slide, that or across, the interest area, right? You can capture that image. And for this machine, actually has a pretty cool function. Yeah, they can do the panorama, so they can stitch, the images together. In other words, the size of the image is not limited by the size of the probe. You can scan the whole leg, if you want. So, but sure, we use that function for different studies. Not here, just want to point it out. Okay. Okay, that shows you the experimental setup, and then the data analysis. Pretty straightforward, right? We collect the torque signals, we just kind of like clean it up and filter that. Sonographic images, basically. We use the MATLAB, or you can also use some other, packages. You probably heard about ImageJ, right? There's another freeware out there developed by NIH. It's pretty powerful too. But personally, I like MATLAB, so I do everything post-processing in MATLAB. So, first, generating capacity that was established. I'm going to show you later on, what it means. Then we run the statistics, right? Okay, results. It's coming. All right. So this panel actually shows you, this is a pretty interesting results, and it's not surprising at all, right? Because this actually, there's a couple of circles here. You can see that each circle corresponds to different knee configurations, okay? We start from the knee, full extension, 30, 60, 90 degrees inflection, okay? So that's a lot of information in here, right? So basically, we also have the, you see the blue line, okay? The upper bottom and the lower bottom. Okay, that actually shows you the range of motion, the ankle joint, right? And the more specifically, I'm sorry, that's hard to see. The upper bottom range of motion is corresponding to a 5 newton or resistance torque. So in other words, actually, we use this to compare across, the task condition and participant. So this will allow us to do that more consistently, right? We always pick the same, see that resistance torque. In this case, in the dorsiflexion, we pick 5. In the plantar flexion, we pick 3. You can clearly see that. You see the green one shows the range of motion for healthy control, and the yellow zone shows the range of motion for stroke, right? You can clearly see the reduced range of motion, which is not surprising at all, right? Another interesting thing I want to point out here is actually also have some arrows here. And those errors actually correspond to the so-called neutral ankle position, right? Okay. What it means is actually the resistance torque is 0, right? 0 newton. So that is the corresponding ankle position. We call it neutral ankle position. And you can see the difference between two, right? Across all the knee configuration we tested. Particularly, you can see for stroke that will be in the right. Is actually more toward the plantar flexion, correct? which again is not surprising. We know that typically in the stroke population, you got a equinus, right? Okay, it looks like a horse, right? That's true. And that's exactly what we find here. So not much, new or exciting, right? But this is probably will be exciting stuff, Okay. Since we measure the individual structure of the muscle tendon property, right? I want to show you that. So this is actually the muscle fascicle leg, all right? I should point it out actually using the sonography, that's the level we can get to, right? You can only measure up to the fascicle level, right? Okay, not any deeper than that. But it's still pretty interesting information, right? As you can see that this is actually average across the participant, and the blue one that shows for healthy control, and the right curve that's for stroke. Okay. And again, we got 4 panels here. So the first one corresponds to the knee full extension at 30, 60, 90 degrees inflection. Okay. And then we move from the ankle from plantar flexion to dorsiflexion. You see that? That's all the combination we tested in the study, right? It's a lot of combination. But if you compare that across all the test conditions, the interesting part is actually we also highlight the zone and the area actually or shows the statistical significance. Okay, we highlight in the light yellow. Okay. So you see the area like that, that means, there's a statistical or significance between the control and the stroke group. Interestingly, you see that pattern is pretty consistent, right, across all the knee configuration. And simply tells us actually for this group of population, okay, stroke, they have a significantly shorter, okay, muscle fascicle leg, right? Yes, questions? Go ahead.
Is 0 the neutral position in each of the figures up there? Is that what 0 would mean?
0 here, that would be the, well, let me explain that. This is actually slightly different from here because this is like a 90 degrees. You're right.
Okay. Yeah,
that would
just
be
in a regular.
Yeah, exactly. We call it neutral, but the neutral we define here, that corresponds to 0 resistant torque, and not necessarily to be at a 90 degrees. Yeah. That makes sense? Yeah, sorry about that.
No, it's okay. I'm just trying to.
It's a little bit confusing, right? Yeah. Any other questions? Yes?
It's really interesting to see that the significant results are more for the 60-degree flexion as compared to the 30-degree flexion. So the C plot is more significant than the B.
C and B?
Yeah.
Uh-huh.
Comment about that. Why is that the case? To me, seem like it should just follow a descending track, like, you should find more significant differences in the extreme conditions A and B, and not so much in B and C. So what's happening there with the muscle property?
Well, I think there are a couple of things going on here. You can think about, when we're using the sonography, it only slides or measure in the one particular single plane. Okay, it's not actually going to give you 3D structure. Okay, and even we try to do the measurement or assessment consistently across test conditions, but in reality that's almost impossible, right? You know that you cannot place exactly the same spot, and even you tilt that a little bit, you're going to get a different measurement. So I think part of this is due to the measurement. We'll see inconsistency or variability. Because you're not tracking exactly the same, for example, muscle fascicle. But like I said, if you're tracking exactly the same muscle fascicle, you're probably going to see that pattern, But this will be impossible, in a setup like this, right? You probably have to dissect, and pull out that particular muscle bundle and measure that directly, Other than that, it's current technology, I think, will not be able to let us do that. But you're right. That you can see that is not a that systematic, but at least it shows the trend. You're right. Yeah. That was a question. Kind of. Okay. Any other questions? All good? Okay, let's move on. Okay, next I want to show you the passive ankle joint torques, right? Since we measure the ankle resistance torque, again, you know, across all the cast condition, right? Again, the full knee extensions, 30, 60, 90 degrees in flexion, right? And plantar flexion to dorsiflexion. Okay, you can see that this is just simply the resistance torque, right? We measure. And the pattern is also clear, right? Okay, you can see that a stroke actually have the significant higher resistance torque, okay, and compared to the healthy control in most of the past condition we do. And then what we can do further is actually we can take the first derivative, right? We can calculate the slope, and in other words, we calculate the stiffness, right? We can calculate the slope, okay, the grade or whatever. And then we can do similar things, right? We can compare the ankle stiffness, right? This is probably will probably give us a more meaningful interpretation. Okay, that's important mechanical property, right? Okay. Again, that shows actually the stroke group actually has a higher joint stiffness when compared to the healthy control. So now we actually already show you some of the findings here, but we are curious to step further, right? We want to establish the force length relation, as you probably learned in other courses, right? Muscle mechanics and those kind of courses. You probably see the typical force length curve, right? Either under passive or active condition. So that's what we want to do, right? But since we cannot measure the muscle force directly, so we have to make some assumptions. Luckily, actually, you see that because of the unique design, this is actually anatomically, right? You see that the gastroc, we all know, is a biarticular muscle, right? It crosses actually both the ankle and the knee joint. And the soleus actually only cross the ankle joint, right? So that gives us some hope and promise to isolate, see the contribution from each muscle, right? Okay, so what we did is actually we find the difference in between, you see that? Because remember we test from a knee full extension, right, to a knee flexion of 90 degrees, right? So if we calculate the difference in terms of the joint resistance torque, we can calculate actually the contribution or isolate the contribution from gastroc events, correct? Because when the knee is bended, actually, you see that, or full extended, you see the contribution from the soleus will be the same, right? It doesn't cross the knee joint. And the only difference here is actually is due to the gastrocnemius muscle, all right? So by doing that, we can isolate the contribution from gastrocnemius muscle. But another problem we face here is actually we're talking about a medial half, right? The gastrocnemius. And there's a lateral half, right? There's two halves, right? So we have to make another assumption, or this is from a literature, we have to find out the contribution from each of the muscle half, right? So we figured out, okay, calculate the corresponding muscle force, and it's plotted here against the muscle physical length. Actually, we measure using the sonography. Okay, this again, that's the group average. You can see the pattern shows it's completely different, right? Okay, and this is the stroke in the right, and the green, that's the healthy control, right? And for sure, we can do. We can also calculate the slope or the stiffness here, but you can tell easily that it has a steeper, right, slope and a definitely higher stiffness, right? They do that, okay, at the muscle physical level. All right, to summarize this part, what we find here in this small study, okay, the stroke had a shorter muscle physical length, right? As I show you, it's confirmed, and I didn't show you, but actually I want to just point it out. We also measured the Kinesiology, right? So there's a couple of things you can do. Muscle thickness or Kinesiology, right? It's all related to the muscle mechanics. It also shows the smaller Kinesiology, all right? And the ankle joint biomechanically, we find out actually stroke had a higher resistant torque and a joint stiffness, all right? And we believe actually this actually gives us some indication, right? Suggestion that the increase in joint stiffness is attributed to the muscle physical level, okay, or changes. All right. So that's the first study. Any questions so far? Yes.
Perhaps I missed it, but how long post-stroke incident were these subjects, and had they completed, you know, their any kind of rehabilitation strategy? How long since their stroke?
How long? Well, here's the thing. You know, this actually the group we recruited actually at least 1 year post the stroke. So it's definitely chronic. You know, so typically study, let's see, post 6 months, right? It's pretty chronic. You know, and typically they only do the in-hospital treatment or rehab in the first maybe 1 or 3 months. Yeah, we got a PT maybe can answer that better than me. But after that, actually, typically they're going to use the assistive devices. For example, ankle orthosis, yeah, to help them improve their mobility, right? So some probably use the cane or things like that, to help them to work around. But most of the, I think if I remember correctly, majority of the participants we tested in the study are not including any rehab or a program at the time. Yeah, that's far as I remember. Yeah, right.
Is this information, I saw that was published in archives of
Correct.
physical medicine rehab?
Yeah.
Do you think it's influenced any rehab practices for stroke? I mean, can part of this deleterious effect be prevented by some type of rehab?
Well, that's a good question, and honestly, I don't think that one study will impact the whole clinical practice. It definitely needs it will probably just offer a piece of information, and many studies or a larger scale study will get what we call clinical, right, randomized clinical trials, all those kind of things will have a sufficient power, statistically power, right, to hopefully impact the clinical practice. At this point, I cannot see that. Yeah, this is only one study, a small scale. We tested 10. You can always see, okay, that's under sample. Statistically, it's not the power is still the question, right? So, I mean, yeah.
Can I just add to that?
Yeah.
So, but I think this is a great assessment tool. I mean, getting such a deeper understanding of how you measure joint stiffness. So it can be used as an adjunct to the intervention that I can give them for improving ankle function in individuals with strokes to see what's going on at the muscle level.
Do most stroke survivors that present with this, is it almost automatic they get an AFO, or is there any other type of device that's given to them to assist?
Not everyone will get an AFO. I mean, there are so many other modalities that are available. For example, functional electrical stimulation. That's it depends on the level of severity. Do they actually have some active control, and are they good candidates for functional electrical stimulation, or is it just passive support that we need? So I think there are a lot of things to consider when we're designing their intervention.
Thank you.
Any other questions? We're all good? Okay. Thank you. Okay, let's move on to the second study. We're probably going to speed up a little bit, right? Got like 20-some minutes. Okay, the second study actually already show you the experimental setup. It's pretty much the same, right? Just want to show some of the details about the methodology here. What we did in this part actually we used some of the parameters. We have turned from like a commercial software. In this case, it's Sync. And nowadays, you probably heard about there's OpenSim out there, right? It's a free platform. You can do the muscular skeletal or modeling. Okay, it's a pretty powerful one. I encourage you to download that. That's developed by the group at the Stanford University. By the time I think we got access to this, so yeah, we just use that as a commercial one. But it's more expensive. But I guess the similar parameters number you have. And then we actually calculate the muscle force, right? So you see that is actually all based on what we get in the study, right? This is the angle is actually the Kinesiology angle we measure in the study. This is all subject or dependent, right? Okay, it's not based on assumption. Yeah. And then we have normalized the force. That is an important step because otherwise we cannot compare it across the cast condition or participant. Okay. And the force generating capacity. This actually was modeled using this or a simple model or formula. You can see this exponential, right? Just kind of like a valve shape. I'll show shortly. So okay, here's what we get. All right. So if you plot the normalized muscle tension, again, this is at the muscle physical level, right? If we plot that against the muscle physical length we measure using the sonography, and this is actually shows the two groups. Okay, we got a control in blue, we got a stroke in right, and then we also identified the physical length actually corresponding to the peak muscle tension. Okay, this is called the optimum physical length. Okay, as shown here on the top. You can clearly see the difference between those two patterns, right? The force generating capacity, and this is actually the active force length relation. Okay, and besides, the passive one I showed you earlier, right? That's more like exponential, but here it's more like a valve shape, right? So you can see the optimum or physical length actually for stroke is significantly or shorter or smaller than that in the healthy control group. All right. So again, I want to point out that we only measure up to the muscle physical level, right? But speaking of the muscle mechanics, you all know that the sarcomere is actually the smallest force generating unit, right, in the skeletal muscle. So what we can possibly do is we can definitely do some hypothetical calculation or assumption, right? We can estimate, the corresponding sarcomere length, right, in this case. So this is what we do, okay? So we actually take the number, okay, from the literature, right? The number of sarcomere in series. That's the number we use. And then we divide it, by the muscle physical length we obtain in this study, right? And here, again, exactly the same pattern, but it's different scale, right? It actually switched to the sarcomere length, okay? The pattern is exactly the same. And we want to compare to the typical force length curve, right? So the black one, again, that's taken from the literature. You see that published years ago, right? Probably even before I was born. Okay. Yeah. So that's a black thick line. You can see that actually corresponds to our results in the healthy control pretty well, right? Okay. But again, we see that for the stroke, the whole pattern is shifting to the left side, right? In other words, actually the optimum or muscle physical length, in this case, the sarcomere length actually is shortened, right, in the stroke population. Again, this is based on the hypothetical, right, estimation. We need to measure that directly, so we cannot draw a conclusion on that. But it's likely what happened is it's gonna shape. There you go. So most likely what happened in this particular population is due to adaptation, right? The muscle is a highly dynamic organ, right? It's gonna adapt to the mechanical stimulus. So what happened is the number of sarcomeres in series could be reduced. And what happened is the whole curve could be shifted back, approaching or approximating the optimum sarcomere length. You see that? As we see in the healthy control group, right? All right, to summarize this part, I think I already showed you that, or the stroke had a stronger, the smaller optimum physical length. And mainly, or we believe that's probably due to adaptation, right? And what happened is the number of suckers could be reduced, all right? So in that stroke group, most likely the whole curve will be shifted back a little bit, right? But to how much, we don't know, all right? So we need other modality to explore that, right? And measure that directly, even though I know that's pretty challenging, right? Okay. Well, Dr. Rick Lieber, yeah, he actually has done some pioneering work, to measure the suck meters in vivo. But that's a pretty invasive procedure. You have to open it up, put the probe on that. Yeah, he did it himself. I think he showed that in one of the conferences years ago. Just open his arm and put the probe out there and measure the suck meter. Yeah. Speaking on science, right? Yes, sir. All right, that's about the second study. Any questions so far before we move on? Yes.
Stroke general atrophy is also happening, right? So do you take into consideration the muscle size to minimize this controls and stroke? So how is that impacting these measures?
You mean the length of the muscle physical? Not really. We didn't normalize that. We actually have done that. I think it didn't show any difference in that. You're right. You can normalize to the body height, right? To the leg length, or for example, yeah. You can take that into account. But I think if I remember correctly, we did that. Yeah. We didn't find any. But that's actually when we submitted the manuscript. Yeah, there's one of the critique I remember, yeah, from the reviewers. Yeah. So, can we add that into discussion? Yeah, like you said, yes. So we did normalize with respect to the body height. I remember, yeah, but there's the same finding or results. Yeah, correct. But that's a good question. Yeah. Right. You're right. If you have a super tall or short person, you're right. You have to take that into account. Because in the separate study, we also use the similar protocol on the children with the separate palsy. Yeah. And you can see the children actually even at the same age, right? They have a different, stature. Yeah. You're right. You have to take that into account. Correct. Yes. Any other questions, comments? We're all good. Okay. Let's move on to the third study. That hopefully will be exciting. In this study, actually, what we did is actually we did a single session or treatment, okay, for intervention. In methodology, this is actually exactly the same group of participants we tested in the BioMechanical study to show you. Again, we use a similar setup, right? But in this study, we use a different machine. It's called the ankle stretcher, right? It's again, as we customize the motorized control for device, going to show you shortly. And we use the stimulator to activate the muscle and so on, okay? And here shows the setup, right? Okay, so that machine is a lot smaller, right, than the knee ankle setup I showed earlier, right? So this actually only targets the ankle joint, right? Again, inside the box, there is the servomotor out there. You can control the speed and direction of resistant torque, and there's a torque sensor here, which will allow us to measure, how much resistant torque is experienced around the ankle joint. Basically, this is what we did, right? We also applied the electrical stimulation to assess the triceps muscle actually pre and post the treatment, right? Okay, we do the stretching intervention, right? So we do the baseline and also post the treatment, right? So we compare, and there's two conditions to see if there are any effects out there, all right? And again, they use this as a very powerful stimulator, as I showed you earlier, right? Pretty cool device. It's hard to get. More details about our treatment, right? So what we did is actually Okay, speaking the motor control here, we don't allow the motor to run too fast, right? Because you all know in this particular population, if you stretch too fast, you're going to induce the stretch reflex, right? So we try to reduce, avoid that to happen. Okay, we set the speed at most at 12 meters per second, for example. All right. And then we actually break that down into a smaller session. Okay, each session will last about 5 minutes. So we did that for about I think it's 12 small sessions. And the cross section actually we're going to adjust to see that the resistant torque, right? Because you probably the ankle joint will be loosened up, across the short sections. You're probably going to increase that, right? More aggressive. Okay. And here I'm going to show you just kind of like a demonstration of how the treatment was done, right? So basically, the person was sitting in the chair, the foot angle is actually strapped into the foot plate. And then you can see that where the motor is going to cycle that through, right? We're going to set a resistant torque. It's pretty repeatable, consistent, okay? So here we go. The day analysis, there shows you the typical position and a torque, and then we plot them together, okay? And this will give us the so-called hysteresis loop, right? You can see actually the loading and unloading curve, they're not overlapped, right? So there's the energy loss because of that. Typically, if you load like a material like with the viscoelastic property, you're gonna see something like this. And that's exactly true, when you load any soft tissue, right? You're gonna see something like this. So, so this curve actually will allow us to quantify a couple of things. You see, as I show here, one thing we measure or assess or estimate is the index of hysteresis, right? In other words, how much energy is lost, okay, during the loading and unloading cycle. Again, on the top of that curve, we can also quantify the corresponding resistance torque and the stiffness and so on, right? As I showed you earlier. So, next slide shows you how we measured the Achilles tendon, right? We measured the length. We also measured the cross-section area, right? So this can be nicely done using this powerful machine. You can see the image is pretty clear, right? Okay, just wanted to show you some of the results. Okay, the torque generating capacity. Again, this is actually just between the stroke and the healthy, right? The stroke would be right and the green, again, that's for healthy. So this is pretty similar to what I showed you in the second study, if you recall that, right? The force-length relationship pattern, right? Again, this is shifted. But this is actually include all the three muscles, okay, keep in mind. So we activate all the three muscles, all right? Two has the gastroc and the soleus, but it gives us exactly the same pattern, okay? And this is probably the interesting part, right? So we compared pre-treatment scratching and post-treatment or post-scratching treatment, right? And this is, again, that's for the torque generating capacity, right? That's the torque generated by the electrical stimulation, okay, plot against the angle position, all right? So again, this is normalized, right, with respect to the peak torque. And you can see that opposed to treatment or intervention, you can see or significantly increase, right, okay, in the torque generating capacity. A little bit more results, this is probably also interesting. Since we measure the Achilles tendon, right, remember, we can compare that between these two groups, right? You can see that the stroke actually had the smaller, this is the length, actually this is the cross-section area, right? This is the smaller and actually thinner, right, Achilles tendon. And we also quantify and assess the stiffness, right, at different or ankle position, all right? It's corresponds to neutral, that'll be 0, that'll be dorsiflexion 10 and 20 degrees, right? We also see the significant difference, right, between pre and post-treatment, see that? So that indicates that actually the stretching does help, right, to loosen up the ankle joint, improve the force mechanical capacity. All right, to summarize this quickly, so basically show you that a stroke had a shorter tendon, a thinner this tendon, and also we see a similar pattern regarding the torque angle relationship, right? And after this, just one single section or intervention, right? We can clearly see some improvement, right? It's kind of promising, but for sure we cannot draw a conclusion just based on one single session, right? It has to be multiple sessions and long-term effects, which actually was done later on. We improved that, yeah. Okay, it's detected. All right, I think that's about it. Thank you very much. Any questions? Yes.
How long was those effects evident? Like, so when did you test the improved range of motion? I forgot from your previous slides there.
Right after the intervention. Yeah,
The minutes, maybe?
right.
Yeah.
Yeah. That's what I'm saying is more like an acute effect.
Mhm.
Yeah. Right. Yeah. Correct. It's only like one visit to the lab. We do the baseline, the pre-treatment, and then the intervention, and then do the post-treatment assessment. Yeah. To about 2-3 hours. Yeah.
But then your follow-up studies you just mentioned, it seems like there's long-term
Yeah.
improvements if you do, multiple acute bouts. There's this transient effect.
Exactly. Right. Yeah. Yes.
I'm not sure if you're familiar with the local mat device or heard of one.
Yes. The RSC actually we did have one.
Okay. Have you guys seen any relationship of using these methods pre-use of local mat, or do you guys correlate the two in rehab?
Well, honestly, at that time, it's different, run by different labs. We haven't worked together that much. But what I can tell you is actually in that group, they add another attachment or accessory to the local mat. Actually, they can move the ankle joint. Actually, yeah, you're right. So basically, essentially, you can integrate that two together. You can do like a local mat or locomotor training, and on top of that, you can add in some ankle or powered ankle device like that. But nowadays, I think most likely you're probably going to use like an exoskeleton to do that. It's a lot easier, but yeah, it's expensive. Right, that's good thinking. Yeah. No, we haven't done that. But you're right, and speaking of locomotion, walking is definitely a coordination across all the joints. Yeah. And here we only target one joint. Yeah, the reason for that is simple, right? Because speaking of research, you don't want to target the whole body, right? Or 600 some skeletal muscle. There's no hope we can do that, right? So you have to focus, narrow down, your research question, and start from there. But you're right. Nowadays, I believe, they all use well, at that time, I think when I was at RIC, now they changed the name, but I think a rehab robot actually was one of the hottest things people were working on. Yeah, so they developed all kinds of different robots to help the patients to restore that function. Yeah, both upper and lower. Yes. Yes.
Just following up on previous question, so how much was the carry over from one session to the other, and how many sessions does it take to actually change the properties of the muscle that had a carry over to the next session?
Well, here's the thing. We run like a 12 short session, like I said. We didn't assess in the middle. You see that? In order to do that, you have to assess every single session. That will probably run a whole day, I'll tell you. It's a lot of work, So yeah, if we did that, we'll probably can tell the trend. But I think most likely it's happening gradually. Yeah, I think that's mostly that's the case. Yeah, it's not going to happen suddenly. I can tell you. Right. Speaking of rehab or exercise, or outside of training. Yeah. Right. Any other questions? Comments? Right. Thank you.
Thank you very much.